Okay, we continue with lab 3. I'm sorry I had to stop abruptly due to some problem with my pen. So what we have seen so far is that if we evaluate this integral 4 dx by 1 plus x square, that will give us pi. Of course, the limit is between 0 and 1. So evaluating this integral amounts to finding the area under the straight line between 0, this is 0, and this is 1. This is a well-known fact in calculus, which is called the Riemann sum, but as I have repeatedly said that if you are not familiar with calculus, it's not a problem. Basically, we have to somehow evaluate the area under that straight line between 0 and 1. Now, one way of doing that is to divide that area into many small and thin rectangles and compute the area of each of those rectangles and add them up. So that's exactly what I have done here. I have divided the area under that straight line into many small rectangles. As you can see, this is, for example, a rectangle. Now for this rectangle here, I have indicated its height as b and its width as a. So this is a and this is b. Now how do we know the height of this rectangle? Basically, you have to evaluate this function 1 over 1 plus x square at some point where the point is somewhere inside this rectangle. Now one way of doing that is of course to choose the midpoint of this interval. This is the base a and midpoint of the interval, and whatever is the coordinate of that midpoint, replace that value for x and you get the height b, this height b. Of course the width is a and the width is under your control. That is how finely you will divide this interval between 0 and 1 will give you smaller and smaller widths. Why would you want to divide it into very fine intervals? Because if the intervals are not fine, in other words, if the intervals are coarse, then you miss out on some part of the area. For example, here, this part of the area you see, here the intervals are very coarse. So if I compute the area of this rectangle, then I miss out on this part. And more you miss out, the less accurate your approximation of pi will be. So intuitively you can see the way to avoid missing out on these small parts is to make the rectangles thinner and thinner. Thinner the rectangle, the less parts will be missed. And when it is extremely thin, you will get a better approximation of pi. And exactly what we do here, we divide the area under the straight line into many small rectangles, and we'll evaluate each rectangle, the area of each rectangle at the midpoint of its base and add them up. So we need a variable to store the sum. When I say add them up, add these areas actually. So there we need a variable called sum where we will store these areas. And at the end, we'll basically get the value of pi by looking at the sum, which will come in a little while. So the key thing, as you have realized now, is to decide on the number of intervals. And we have seen that more the number of intervals, the better the approximation. Let us call the number of intervals as num steps, and we'll gradually increase these variable num steps and get better and better approximation of pi as num steps becomes larger and larger. So let us start with num steps equal to 1000. So we have to divide the interval between 0 and 1 into 1000 parts. And you know that now we have to evaluate the area of each of these thin rectangles and add them up. So your code will look like this. I have declared these two variables here outside the main, but you can declare them inside the main as well. In fact, it is better to declare them inside the main. So inside the main, I have a variable called I, and I have a variable double or few variables of type double, x, pi, and sum, which I have initialized all to 0. And if your num steps is 1000, the width of each rectangle will be 1 over 1000. You can see intuitively that should be the case. And why have I written this double here? Because this is called typecasting in C. Because num steps is an integer and step has been declared as a double. So for every expression that you use in a C program, the type of the left-hand side should match the type of the right-hand side. So when I do this division 1 over num steps, I cast the type of num steps from integer to double, and then I divide 1 by that double, and I get the width of each individual rectangle. So your basic program will look like this. Now, if you can write it in many different ways. Basically, since there are many rectangles, we have to have a for loop. Intuitively, you can see that. And the for loop should iterate from 0 to num steps minus 1 due to the way the loop variables work in C, and or due to the way I have chosen it. I equal to 0, I less than num steps, I plus plus. Now here is the evaluation that you are doing at the midpoint of each of those rectangles. Because I is the loop variable, you have to add 0.5 to the loop variable to reach the midpoint, and you have to multiply by that with step, because that will give you the correct midpoint. In other words, since you have divided this interval between 0 and 1 into many small parts, each part has a value of I associated with it, and you are adding, for example, if this part is 10, so 10 times I plus 0.5 will give you the midpoint of the 10th interval. So that's what we are doing. We are evaluating the midpoint of each interval here, depending on the iteration of the loop. And here I am adding up. So this is the evaluation of that function 4 over 1 plus x squared by replacing x from here, and I am adding that up. Now you may say that this is not really the area, because I should multiply the height of the rectangle with the base of the rectangle. Now all the bases are same. You note that when you have decided on num steps, your step is fixed, all the bases are of size step. So there is no point. If you want, you can multiply by step here, but also you can multiply at the end by step by the overall sum to get the value of pi. So this is the basic structure of the program. You have to first implement this program in C. It's a sequential program for evaluating the value of pi or approximating the value of pi. And from here on, we'll use OpenMP to parallelize this code or make it multi-threaded.